So let me introduce you mathematically that how it is happening. So in gradient descent, mathematically what is happening, like let's say this is a mean square error. So we have introduced one of the term that was sum of a square error. So in sum of a square error, what was happening, this is the term that was the sum of a square error. But if you add that term 1 by 1 n to that, it becomes the mean square error. Why? Because the number of points, the number of data points that you have, you are dividing by that number, so it becomes a mean square error. So this is one of the also term now. So like if you find out the minimum of that function, or even 1 by n multiplied by that function, the minimum value will be always same, because this is a constant term that we are multiplying. So why we are multiplying that constant term actually, but yeah, this is what we are getting, like mean square error to we have to minimize that mean square error function. So this is actually the function that we have, and this mean square function is actually called what, cost function. So in terms of gradient descent, like we call that cost function. So in ML, like in every algorithm you will be learning about the cost function. So in every algorithm, if you are finding out that how much efficient it is, how much accuracy it is having, so to reach the maximum level of accuracy, you have to minimize the cost function. As much as you can minimize the cost function, your model will be, your algorithm will be working more better. So this is the concept behind that cost function. So you can see all of the terms, like n is the number of data points that we have, and yi is the observed value or the actual value that we have, and yi cap is the predicted value that we have. So you already know that thing. Now again, the same thing, like you can see, just MSE is represented by f of mb, because this is a function of like m and b. So I have told you know the function of beta naught and beta 1. So this is the same thing that we have, but instead of beta naught we are having m, and instead of beta 1 we are having b. So this is in terms of, like, if you know the equation of a straight line is y equals to mx plus c, here actually b, so we are using actually b, so mx plus c, so sorry, mx plus b. So the same thing we are using here. Here you can see y I cap is replaced by mx plus b here. So this is why this function is becoming as the function of m and b, and all the terms are same, like only y I cap has been replaced by the mx plus b. So our goal is what? Our goal is to minimize the cost function that we have. So you can say minimize the mean square error or the cost function. Why we call that minimizing the cost function? Because there are many other terms like sum of a square error I have introduced you. This is the mean square error. There are many other terms also, like mean absolute error also. So all of those are different metrics of finding out the errors. But after finding the errors, you have to find out the minimum value of that error. So cost function is the general name that we give for that function. So we have to minimize that cost function to find out the minimum value of the error. So again, the question is still that we have is the how to minimize the cost function. So let's say this is the cost function that we have. Now you can see this is the gradient descent approach that we have, and this is for actually a single variable. So let's say this is the cost and this is the weight that we have. So what is the weight and cost actually? So if you take any straight line y equals to mx plus b, so what is m actually? M represent the slope and b represent the intercept. So this is the intercept value that we have, and this slope is actually also called weight. So this is, so there are many terms that we actually introduce here for just representing m. So don't be confused. We can say like in terms of a straight line we call that slope, but when we are having like in like machine learning, these are actually called weights, because these are giving weights to the feature. X is a feature and this is multiplied with the x, so it is giving a weight to that feature. So that is why we call that weight. So you can see now this is a graph of what, cost and weight, and if you take m as a weight, since we are squaring, what is happening, m will be a square. So in whatever the final function that we are having, so we are not going into like detail what will be the actual final equation that we have after squaring, but yeah, we know that m will be squared. So if m will be squared, and there will be also like m terms also, since a plus b the whole square is a square plus b square plus 2ab, so m term will be also there. So obviously the equation will be what, quadratic equation, it will be having m square, and the graph will be like a parabola. So this is the simple parabola that we have. So whatever the orange function that we are looking at here, this is the cost function that we have. So this is the whole cost function that we are representing using that orange line. So where is the minimum value of that cost function? Here now, this is the minimum value that we are having. Now you have to find out the value of that m and b for which this is the minimum value. Now what you have to do, you have to find out the value of m and b for which it is having the minimum cost value, like here. So like what happened in gradient descent, we actually start with any random guesses, like if we, generally we take like m equals to let's say 0.01 and b equals to let's say again 0.01. so you can take 0.001 also, very less, so that it will be safe for us. So let's say it is starting from here, this is the initial weight that we have. Now you have to reach towards the minimum value. How you are going to reach? You will find out the slope at that point, and this slopes decide actually that you have to go in the left direction or the right direction. Now after defining that initial values like m and b, how we are going to update that value? This is one of the questions that we have, and the answer to that question is this one. So this is the formula that we use to update the values. Like here in terms of beta I have represented, but if you take that in terms of n, m and b, so new m will be what you can say m dash, let's say m new is the m dash, and this is the m, the old one. This is what minus alpha into, you have to take the derivative of f of mb with respect to what, del of m, because you are finding out new value of m. Similarly b dash equals to b minus alpha del of f of mb divided by del of b. Here minus sign will be there. Now you can see how wisely that formula used to find out the new values of m and b. So initially you have started with 0.01 and b equals to again 0.01. Now what will be the new m? M minus alpha. Alpha is what? The learning rate, and del of f of mb with respect to m is what? Derivative. So again relate that concept to the concept that I have introduced you earlier in gradient descent. So what was the factor that actually matters reaching to that minimum point? The slope, the value of slope, and the step size. The slope and the step size were the two major factors towards reaching that minimum point. So again here also that slope, the value of slope, you are finding out using that equation, del of f of mb with respect to del of m for m, and for b del of f mb, like you can simply say del of f with respect to del of b, because you are finding out the new value of b. So this is the derivative value, and alpha is the step size, that means the learning rate. We in terms of gradient descent we call that the learning rate. So what does the alpha do? Alpha decides you how rapidly or slowly you want to reach out to the minimum point. So you have to choose alpha by yourself. Like this is an iterative approach. You have to start with any random value like alpha, maybe alpha equals to again 0.01, like that, like a small value. And if it is taking very large number of like the steps towards reaching that minimum point, you have to increase the value of alpha so that it will reach faster by taking a larger step size. Now how you will decide that step size, I'll be telling you in a while, just wait for that. But before that you have to understand that how actually you are getting towards that weight using that formula. So you can see how wisely that formula used, like m minus alpha. So you can see now after finding out derivative, and learning rate will be always like positive, so you are having a minus sign. Minus sign represent the whatever the slope value that we are having, you are having a minus sign with that. That means if it is having a positive slope, so you can see now for here, for this point, the slope is what? Since it is less than 90 degree, the slope will be like, if you extend that line to here, this is the slope that we have. Let me represent that with the red line. So if I extend that, yeah, this is the value of angle we have, and tan theta will be what? Tan theta will be the slope of that point. So you can see it is always positive. Since it is positive and multiplied by negative, so you are subtracting a positive number from a m. So m is initially what, 0.01, but since you are subtracting, m value will be what, it will be reduced by what factor, alpha, that means the learning rate multiplied by the derivative, like the slope value. So let's say this is the value that is coming, and this is called actually a step size. So after finding out the value, you are subtracting from m. So let's say it was 0.01, now it is having like 0.00 let's say 8. So this is the new value that you are, so this is the new value. So this was the old value and you are reaching here. So this is a new value that you are having. Now again the slope will be what, the slope will be again positive, but it will be a little less value. So that means what, the step size will reduce. So that is why you can see a step size is reducing. So as you reach towards the minimum point, the step size will be what, it will be reducing, because the slope value is reducing. But again, that alpha value is the measure factor that we have, because if you take initially like a large value like alpha equals to 2, what will happen, like instead of coming here, like it may go directly here, but it may also go from here. Instead of coming to the here, it may go directly here. So from here to here, it may jump here. So this is again a bad value of alpha that we are taking, because if you take the large value, it will be not going towards the minimum value. Like the similar thing that we have understood, if you take the large steps here, like if you take the large steps like coming here, if you take a large step to jump here, you will be missing that minimum point. So again the same thing is happening here. If you don't take that optimal step size, it may jumps from here to here, like it may jumps from here to again here and something here, but you will be not getting that minimum point. But I think the concept has been clear. Like this is the initial weight, this is the incremental step, you can say, this is the gradient value, this is the minimum value, and this graph is actually what, the cost plot we are having with respect to weight. Now I will show you separately like how this learning rate, that means alpha, is very important for us. So we have to get that optimal value of learning rate so that it will reach up to the minimum point. Let's say you are having too low size of that learning rate, that means alpha is very low, let's say 0.0001, like that. So what is happening here, you can see now, a small learning rate requires many updates before reaching the minimum point. So it is having like many large number of steps. So the computational power of the computer will be used more aggressively as compared to the other like just write and too high values. So if you take too high values also, like I have told you the problem, instead of reaching towards the minimum point, it may jump from here, then from here, and it may jump back and forth, and it will not come to the minimum point. So you have to find out the just right value of the alpha. Let's say alpha equals to 0.05 is the just right value, and alpha maybe 2 is the very last value. So this is the optimal value that you are having to reach at the minimum point at a minimum number of steps. Now how that value is decided actually, so again I have told you that this is a simply iterative method. You have to start with any alpha value, you have to check the number of steps. Like after applying that machine learning algorithm, you can use the Python coding to understand, like you can print each of the times the steps is taking. So you will be actually getting the count of steps that has been taken to reach from this point, let's say this point, to the minimum point. So if this count is very large, you may understand that like the number of step size, like it is taking very large and the alpha value is too low. You can increase that a little bit, and you can also observe the value of that cost function. So the cost function is actually f of mb that we have, and the value of that cost function you can also plot for different value of alpha. You will be getting, like for each step you will be having the value of m and b. So taking that values m and b, you can actually get the value of f. So f at every step size, that you can print the value of that cost function, and you will be getting that after certain steps, like the value of cost is not decreasing, so it is becoming constant. That means you have reached to the minimum point, still the steps is going on, so that means the alpha value is too low, so you have to increase a little bit. So this is how you interpret and get the optimal value of alpha. Yeah, so guys, this was the concept of gradient descent that we actually used to find out the minimum value of sum of a square error. So using that gradient descent, what actually we are finding, we are finding out the value of m and b, for which the value of function, that means f and mb, or you can say the sum of a square error or mean square error is having the minimum value. So if the error is minimum, the equation of the line will be the perfect fit of line. That if you have many data like here, so if you find out the value of mb, you can plot that line, and this will be the perfect line fit, like best line fit for that data set that you are having. And in this way you can solve the problem, like predicting any values in future. You can predict for any x values, you can predict the y values easily. Now there are like assumptions in linear regression. So whatever the relation between the dependent and independent variable that we have, this should be linear, almost linear, because we are finding out what we are finding out a straight line fit. So if let's say your data point, instead of linear, let's say the data point is representing here, let's say this is the data point that we are having. So you can see now, if you take the best fit line, it will be not actually a line, instead it will be a curve. So this is not a perfect regression problem. That means we can't use linear regression in here, because if you take a simple line here, if you find the best fit line, it will be always missing some of the values here. So these values are missed now. So this is not the perfect fit line. So that is why the assumption is what, it should be always linear, not actually linear but almost linear, like dependent and independent variable. This is the relation, and this is just for the single variable, let's say x and y. So y is the dependent variable and x is the independent variable. So this is the single variable that I have represented, but it may have n number of variables. That is actually called what, multiple linear regression. So whatever the example that we have seen here, like all we have seen in terms of linear, simple linear regression using the simple m and b terms, but like m is for the feature x, mx, so single feature that we are having, but it might have more than one feature now, it might have a multiple linear regression also. So this gradient descent works in that case also, but just for the sake of understanding we are just showing it here, a simple linear regression, because we can't plot the multiple dimensional plots here in 2D. So we can max to max we can represent a 3-dimensional figure which is having a two features, actually two features and one dependent variable. So this is the, let's say, 3-dimensional figure that we have. This is the x1 feature and this is the x2 feature, and y is the dependent variable. So this is the maximum dimension that we can plot and show here. But in regression we can have multiple linear regression which may have like more than hundreds of features, and it can solve that also. Cool. So this was about the first assumption. The second assumption is mean of residuals should be 0 or close to 0 as much as possible. It is done to check whether our line is actually the line of best fit or not. So like the same thing, the sum of mean of residuals means what, the sum mean absolute error, mean sum of mean square error actually. So we have to take the mean of that residual to us 0. So this is the problem that we actually solve to get the best fit line. Third is what, there should be homoscedasticity or equal variance in regression model. This assumption means that the variance around the regression line is same for all values of the predictor variable x. Now what is that homoscedasticity? So I will be like showing you what is actually that thing. So you can see now, let's say these are the data points that we have, orange value, and this is the best fit line that we are having. Now in homoscedasticity you can see now, those values, those data points are uniformly distributed, while in heteroscedasticity you can see those points are not like uniformly distributed, like at the end this is distributed like that, while in the middle it is not actually distributed at the similar fashion here. So it is actually taking a dumbbell type of pattern, like bow tie shape actually that is called, and this is like random cloud that we have, and this is again an example of heteroscedasticity. You can see this is the distribution is like more here, but it is reducing. So this is a fan shape actually called. So how we deal with that heteroscedasticity? If you have like heteroscedasticity in your data, what you can do, you can apply those transformation, actually log transformation, then you can remove the outliers, like there might be outlier values that you can remove. If you know about exploratory data analysis, EDA, or data wrangling technique, we actually use that to remove the outliers. So we can actually use the technique to remove those outliers, and we can get the you can convert that to homoscedasticity. And we can also try polynomial fit. So polynomial fit means what, like instead of line we can have a polynomial or a curve fit. So these are the solution that we can actually apply towards homoscedasticity problem, not problem like if the data is not having homoscedasticity. The fourth one is what, there should not be multicollinearity in regression model. Multicollinearity generally occurs when there are high correlation between two or more independent variables. That means what, that means let's say there are two features like x1 and x2, and let's take not x1 x2. Let's say x1 is actually representing area of like any let's say house. Let's say this is the plot that we have. This is breadth and this is length, and this is area x1. Let's say three variable x3 also. So x1 x2 x3, x1 is representing area, x2 is representing b, and x3 is representing l, length. Now you can see this area is actually dependent on that na, like area, you know, a equals to l into b for rectangle. So since area is dependent upon that b and l, it can't be an good independent features, because in linear regression that is one assumption that we have, that it should not high correlation between two or more independent variable. So these are independent variable. Let's say we are predicting the price of that plot. Price is the target variable that we have. So this is the y we have, and these are the x features that we have. Now since area is actually dependent on b and l, we can't have that as a feature, and we have to remove that feature because it is dependent on that. So we have to take only b and l. Since these are two independent features, these are not correlated to each other, so that means these are a good fit for applying a linear regression to that problem. Yeah, so that's it guys. This was about the linear regression that we have learned in this session. So from the next session we'll be like covering up advantages and disadvantages of linear regression, and along with that we will be moving towards like polynomial regression and different other types of regression that we are having. So I hope you have understood everything in this session. We'll meet in the next session soon. Thank you.